Welcome back, bio students, and happy Thursday. This is our second take at this video after the other one didn't work too well the other day like the first video. Just a reminder that if by any chance you're watching this sometime before 11:30 a.m. on Thursday, there will be an extra help meeting in Microsoft Teams at 11:30 a.m. on Thursday. So if not, the next one is Monday at noon. Today we're going to finish up something that we didn't get to see the other day. We've been talking about DNA, its structure, how it copies itself, how it's used to make proteins, and how it relates to two different types of this other related molecule called RNA. Today we're going to address what happens when that information stored in DNA undergoes some changes. We miss you, Ziggy, every day. And on that note, let's get to it. To refresh everybody's memories, we did this the other day, but let's just go over it again quickly. So if we were going to film this thing from your homework the other day, let's start up with GAT here with the DNA, because that's one that we're actually given as DNA, where the rest of the row is pretty blank. So if GAT is our original DNA sequence, then the mRNA will be the complementary base to G, which would be a C, the complementary base to an A, which was a U, and the complement to a T, which is A. So it would be CUA as our mRNA sequence. Now, remembering from our chart over here that messenger RNA is really the only thing that matters when we're figuring out what our protein is, I'm going to go right to that chart and look for the letters CUA. C is my first letter here. U is my second letter. So for the first base and second base places, I now know I'm looking in this box right here where they match up. And the third letter being A, it doesn't matter because all four of them give us the amino acid LEU. So I'm going to write that right down here in the amino acid row. LEU, leucine, is the amino acid. If I want to fill in the tRNA anticodon also, it's just sort of going backwards. So from CUA on mRNA, I'm going to do the exact same thing. So C would go to a G in the tRNA, U would go to an A in tRNA, and A would again go to a U in tRNA. So again, as I point out the other day, DNA and tRNA look very, very similar to each other all the time, just that the DNA still uses T's and the RNA obviously uses U's. I pointed out this the other day, tryptophan being the other example where it was just TRP. This tryptophan is the amino acid. I can go backwards and see that the mRNA sequence to make tryptophan is UGG. So I'm going to fill that right in here for mRNA. Again, mRNA being the one on the chart. So I could write here UGG and work backwards, which means my DNA would have been an A, which gave the U, and two C's, which gave the G's. So it was ACC is my original DNA. If I want to again fill in the tRNA, I just got to go again kind of ahead from the U would be an A, and the two G's would call in C's on the tRNA. So once more, the tRNA looks very, very much like the DNA. So we don't have to do the other two columns we did the other day, but this is just what we did the other day. This is normally how it's supposed to happen. When everything's working perfectly, you get your DNA, makes a nice small mRNA copy. That gets used to translate the recipe, and the ribosome then knows what amino acid it needs. It's great when it works this way, but it doesn't always work this way. And that's actually sometimes a really, really good thing.
Mutation. Mutation. It is the key to our evolution. It has enabled us to evolve from a single-celled organism into the dominant species on the planet. This process is slow, normally taking thousands and thousands of years. But every few hundred millennia, evolution leaps forward.
Thank you very much for that nice introduction, Chuck. Couldn't have said it better myself. So this is a word you've likely heard at some point, but may not really know a lot about. Mutations are when changes happen to normal DNA sequences. Whatever the letters should be, something happens to make them different. This can be an outside influence like radiation or chemicals that cause it, or it can be a simple matter of your cells just making a mistake when DNA is being copied or proteins are being made. So in that situation, it's really no different than a typo. The wrong letter was put in, and if no one proofreads and catches the mistake, it'll continue to be there and end up as a normal part of the DNA. That can end up being actually really good, which is why we have lots of different variations in our populations, why we'll look very different, and why we're different than single-celled organisms. That's a really good thing. It could be deadly, where a little mutation causes an organism to die before it's even born, or really anything in between, just depending on how things actually play out. Take this DNA sequence here. TAA, CTG, CAG. So we've got 9 bases, 9 letters. We're in this 3 different sets of 3. So that's 3 different codons from what we've been doing the last couple of days. So this would eventually code for 3 different amino acids. But maybe something happens and instead of this correct sequence here, a mistake is made and the DNA ends up looking like one of these. So maybe it looks like instead TAA, CTA, CAG, or TAA, TCG, CAG, or TAA, TGC, AG. Now I've underlined and bolded the differences, but how did each difference actually happen? What changed here? Take a second to look at these, compare it like you would have done maybe in some kind of highlights magazine or those puzzles where you have to find the differences between things. Take a second, pause the video, and then we'll go over and see what happened here. So in the first example, we can see that where there should be a G, there's an A instead. Everything else is normal, but looks like one letter was removed and another one put in for some reason. In the second example, the C and the T in the middle little codon section have changed places. They've kind of flipped or swapped back and forth. What about the third example, though? It looks like that C in the middle section sort of moved out of order, right? It was in the first place on the correct example up top, and now it looks like it kind of jumped to the end behind the T and the G. But is that what actually happened here? Why is there only a missing letter here? Why are there only two letters in the end? It seems like there should be something that's not there, right? So what happened in this example? We see an A and a G, but where'd the third letter go? Is something gone? When we look at it, what actually happened is the C that was right here in the first place, that got removed. And all these letters then just got bumped back. It's like if you're in a Word document and just hit the backspace button or delete, everything gets bumped up a spot. So the T and the G now moved into their own little codon with the C that was originally in the third one. That's these three letters right here. And the A and the G that were formerly with the C, they're just now kind of by themselves out in no man's land. And there's nothing, we didn't add any other letters, so there's no third base in this example. There's no third part of that individual codon. So in this case, we took something out. We can see here that there are a few ways that DNA can be changed, but the basic idea is the same. And that's that if the bases, the letters, and the codons are wrong in some way, then the recipe and instructions aren't what they should be. In that case, you're going to get the wrong amino acid added to the protein if it all goes and actually does the job. This will very likely make the protein have an incorrect shape. And as we know from way back when, because shape determines function, this can be a really, really bad thing. The protein will not be able to do its job probably. Sometimes you get mutations, little changes here and there where it really doesn't make a difference. It's a minor change. The protein still functions mostly normal. We'll take a look at that in a minute. But a lot of times this can cause bad things. So if you remember, or just before I say that, because it's even small changes can be really, really bad things. They can have really big consequences. So if you think back a couple chapters at this point, when we talked about cystic fibrosis with the respiratory system, that was the brain pop we watched where the girl had this really thick mucus in her lungs, and it was really like kind of glue-like. It was really tough. It was difficult for her to get out. She'd have a lot of chest infections and things. That disease, cystic fibrosis, is caused by a mutation where it's just 3 letters deleted. So 3 little letters in a huge DNA sequence of 4,440 letters. That's the only difference. One little amino acid missing from a big protein that's normally 1,480 amino acids long. That small difference is the only thing necessary to cause that terrible disease that's cystic fibrosis. So again, tiny little changes can have big, dramatic, bad consequences. Let's take a look at some examples of mutations in a little more detail here. So at the top here we have our normal DNA sequence, AGC TTA CGA. Really, we could break that down into our codons if we wanted. So let's say it eventually gets moved into mRNA, and we'd be reading it 3 letters at a time. So it'd be the AGC, then the TTA, then the CGA. I'll just leave that up there for now. Here we have 3 different sequences that have some kind of mutation in them. So like we did before, take a minute to pause here and figure out what's different about these sequences, how they've changed from the normal, and then we'll see what this all means. In the first example on the left, there's a C where there should have been a T. So up top we had a T right in the middle of this middle codon here, but instead now we have a C. So that's the one change we saw. This is called a substitution mutation. Since one thing is being swapped in for another, you're just doing a substitution as the word is used normally. It's like if you go somewhere to eat and the menu says French fries, but you asked for onion rings instead. That's a substitution. Now, because you're only changing one letter and everything else is staying normal in that sequence, only one amino acid is being affected at most. I say at most because there's some options for what might happen here. If the new code causes the wrong amino acid to be added to the protein, we call it a missense mutation because it's a little off, but it's probably really not anything major. If the new codon tells the ribosome to stop making protein entirely, so if it happens to be a stop codon that we saw the other day, then it's called a nonsense mutation because it's just entirely wrong. It's going to stop it right there. Nothing's going to happen right. And if the new combination of letters just happens to code for the same amino acid that would have been there anyway, just kind of dumb luck, then we call it a silent mutation because, yeah, there's a difference, but it ends up not really making a difference at the end of the day anyway. It doesn't really affect what the eventual protein would look like. On the other side, we have two mutations in which a letter was removed or a letter was added. So we call these deletion or insertion mutations. Deletion, like if you erase something, and insertion because an extra base is being put in that second example there. Right now, I need to point out that while the substitutions on the left only affect one amino acid, these ones on the right affect every amino acid after the mutation. At the bottom here, we can see that changing one letter on the left keeps everything mostly the same in most cases. So if we look back up to our top thing here, the very top normal example, we had an AGC as our first codon. That's the same thing down here that has not changed, AGC. Now we get our mutation in the middle codon, TTA. That changed the middle letter. So maybe this amino acid in the middle is different, but the CGA at the end is still the exact same thing. So we've got our two normal amino acids surrounding what maybe is a different amino acid in the middle. But like I said, this TCA being different from TTA, it may be a little bit off and really not matter. You've still got 2 out of 3, and potentially this is a much bigger protein and be a much smaller percentage, still would be correct. It may be nonsense. So if this is a stop codon and tells the ribosome to stop making the protein right there, then the CGA wouldn't even make a difference, and it would just be only a 2 amino acid protein. That would be bad. We wouldn't want really that to happen. Or maybe even a silent mutation where it really doesn't make a difference. Maybe this was going to be the tryptophan protein, amino acid, and this one little minor change just happened to also code for tryptophan. So maybe that would be the case. That's a silent mutation. It's a change, but it really doesn't end up having an effect on the larger protein. On the other side of things now here, we see everything has changed. So as soon as you get rid of a letter here, in this case of these ones over here, we added or got rid of something. As soon as we get rid of this C, all these other letters here get bumped up a spot. So instead of having AGC as our first codon, now we have AGT. So that's a difference. Instead of having TTA as our second codon, now we have TAC. So that's different. Instead of having CGA as our third codon, now we have GA and who knows what's even in this third spot. That's different. So the entire protein now ends up being different. Adding or removing a letter moves everything up a spot or bumps everything back a spot, and the entire rest of the protein ends up being totally different, and that could be really, really bad. So on the right, again, removing or adding a single letter causes everything to be different after it, and we're going to call this a frame shift mutation because everything just kind of changes what we see in these little boxes down here, the reading frame. Are we looking at these 3 letters, or should we have been looking at, up top again, these 3 letters? It just changes everything. It's like if you're only reading so many letters at a time and now you're just always off by 1. So again, these are called frame shift mutations, and these are typically much worse than a little just substitution like on the left. Can't guarantee it, but typically these would be a much worse outcome. This just needed to be said, right? That's all the new stuff for today, so let's just do some practice and I'll be done. This is the beginning of the second page in your homework, and it's going to be largely similar to what we've done before, but now includes the possibility of mutations when we previously just did regular translation into proteins. So I'm just going to pull up my little codon chart here for a second, and let's see what we're looking at. Where'd my chart go? There we go. All right, so you see here we have an original DNA sequence. That's these letters right here. And then we also have down at the bottom now, or middle of the page rather, a mutated DNA sequence. That's going to be these letters here. So we're just going to compare what's the original normal recipe give us and what mutation happened and what did that actually lead to happening in our mutate sequence and when we make our protein. So we're going to start with the mRNA. If we have a TAC in our original DNA, that's going to go to an AUG in our mRNA. Why don't you fill the rest of that row in and see what we're going to come up with. If I had an ACC originally in DNA, that would give a UGG for the mRNA. TTG gives AAC on mRNA. GCG gives me a CGC for my mRNA. ACG produces UGC for mRNA. And ACT gives UGA for the mRNA. Okay, so that's our sequence right there. Now for the amino acids, we got to see what would actually be produced by the ribosome. So for that, I'm going to go to my chart, And AUG is something we saw the other day. That was actually the start codon, which is methionine. That's always the first one in line. UGG, I have to look this up. UGG is going to give us leucine, LEU. AAC is going to produce ASN. I believe that's asparagine. CGC, where's CGC? CGC is going to give arginine, ARG. UGC would make, where's UGC? Cysteine, CYS. And UGA is the stop codon. So that tells us we're done, and that's going to then release that protein into the cytoplasm. That's what should normally happen. Now we have our mutated DNA sequence. Looks like the TACs are exactly the same, so I'm just going to copy exactly what I had up top. It would have been AUG as my mRNA and methionine as my amino acid. It looks like this is going to be where my mutation is. It would normally be ACC, instead it's an ATC. Let's see if the rest of the protein was anything different. TTG is in both places right here on the third spot. So I'll come back to that later. GCG and GCG are the same right there. ACG is the same in that column, and ACT is the same in that column. So let's just go back to ATC and see what the result of our mutation is. So if our now mutated DNA sequence has a T in that second spot instead of a C that's normally there, our mRNA now is going to be UAG, and I'm going to go to my chart and look at what UAG says. And UAG, UAG says stop, which means this is where the ribosome calls it a day, and none of these ever get made. So now instead of having a 6 amino acid protein that's normally able to do its job, we've got a 1 amino acid protein that got stopped way too soon, and it's going to be pretty useless for any part of the cell that needs to actually do something. So you can see small changes have big effects. At the bottom now it says type of mutation. It was a substitution. We had one letter switched for another one, so it's going to be a substitution mutation right there. It was not a frame shift because there was no insertion or deletion where something got moved. It's a substitution mutation. A C was taken out and a T was put in its place. That's substitution. And what is the effect of that? We're looking now in this little box over to the left here. There was a change, so we can cross out no change. It's not just one amino acid changed, it was a premature stop signal. That was the result of this. So you would fill that out there. One little letter changed, and because of that, the entire protein after that was basically shut down and stopped way too early. So that's going to be our effect there. So this is what your homework's going to be, something just like this. Hopefully it makes sense going forward from here. We only had mutations to talk about today, finishing up lesson 3. So that's it for the week. Go do the form below now while it's fresh in your mind, then complete the worksheets on OneNote. This video should be up sometime Wednesday the 22nd, but posted as Thursday the 23rd. That means if you're listening on Thursday or after, you've already missed the extra help I mentioned earlier. That was 11:30 on Thursday morning. But I'll have another extra help, like I mentioned, on Monday. That's the 27th at 12 noon. This is where the chapter is getting tougher, so please make every use of this resource. Email me, get in contact any way you need to if you have any questions. I know Ms. Vey mentioned she also had some people emailing her. Feel free to do that also. All the work from this week's lessons on translation and mutations are due on Monday the 27th, that same day, on next Monday, at 11:59 p.m., so basically midnight Monday night. And then next week we get to talk about some cool biotechnology and forensics type things like cloning and how to solve crimes. Have a good weekend, stay safe, and keep in touch with each other, and talk to you soon.